Okay, so we will continue today chapter 16. We have talked last time about how to relate velocity and acceleration in several cases, in case we have 2 points on one rigid body, or in case we have a point that has a relative motion with respect to the rigid body. So if you remember, we have started this problem. I will repeat it from beginning. At the instant theta equals to 60 degrees, the rod has an angular velocity of 3 radians per second and an angular acceleration of 2 radians per second squared. At the same instant, the color C is traveling outward along the rod such that when x is equal to 2 meters, the velocity is 2 meters per second and the acceleration is 3 meters per second squared, both measured relative to the rod. Determine the Coriolis acceleration and the velocity and acceleration of the color at this instant. So here they helped you by asking for the Coriolis, because when they ask for the Coriolis acceleration, you will know that you should work with the rotating axis. Okay, but even if they don't ask you this, in this problem, why we should use the formula we introduced last time? Because what do we have here? We have a rod which is a rigid body, okay? And this rod is doing a rotation about the axis. So it's rotating about the axis. So if you take any 2 points of the rod, you can relate their velocities and acceleration by the simple formula we have introduced first, okay? Because it's a one body that is moving. So for example, if you have a point here, let's say A, you know the distance from A to O. You can apply the relations between O and A for translating axis. So you can say that VA is equal to VO. Here, because O is fixed, so VO is 0, plus omega of the rod. So plus omega rod vectorial OA. And no need to add any other term. Why? Because A is on the rigid body. It's not moving relative to the rigid body. However, when you take color C, it's different. Because color C is not fixed to the rod. It's moving on the rod. So it has a certain relative motion with respect to the rotating rod. In this case, the formula you will use will not be this one, which we derived from translating axis. Or also we can derive from rotating axis by just setting that the relative velocity of A with respect to O in the rotating frame is 0. Because if you take a frame with O rotating with the rod, if O is its center and it's rotating with the rod, if you look at A and A is a point on the rod, A is not moving with respect to you. So V relative will be 0. On the other hand, when you take color C, for color C, it's different because C has a relative motion with respect to the rod. So I should apply the formula of rotating axis and I have the relative. So now if I want to calculate VC, I should use the following relation. VC is equal to velocity of O plus omega of the rod vectorial OC, and I should add also V relative plus V relative. So this is the expression that will give me the velocity of the color VC. Now I will start to replace my terms. O is fixed, so VO is 0. Now, as we were discussing last time, we should express all vectors in one frame. Or all vectors I expressed function of small I, small j, small k. Or all vectors are expressed function of big I, big J, big K. And in both cases, you will get at the end the same result because VC is a vector. But any vector, you can decompose it into small I, small j, small k, or big I, big J, big K. So it depends on the problem. What is easier for you to do? Okay? So here first, Let us set the frames. What are the frames that you will work with? We have the absolute frame, which is fixed. So the conventional absolute frame, big X, big Y. And we will take a small frame attached to small x, small y, small z, attached to the rod, the rotating rod. Okay? So here, let me clear it to become simpler. So here, if you want big K is, big Z is perpendicular to the screen, like this. Now for small x, small y, small z, I will take if the frame fixed to the rod. So I can take, for convenience, to simplify calculations, I will take I-axis along the rod. So small I vector will be along the rod, and small j vector will be perpendicular to the rod. So this is small I, and this is small j. Now concerning small z and big Z, they are coincident, okay, because both are perpendicular to the screen outward. So if you want here, small k vector is equal to big K vector. However, for the other one, I can change from one frame to the other by projecting vectors. So for example, if you want to move from small ij vector to big ij vector, all you have to do is to express vector I and j, function of big I, big J. So this is big I. This is big I and this is big J. Okay. So we can decompose, for example, you can say that small I can be transformed into big I, big J by doing the decomposition. Okay, so if you project on X, it's positive. If you project on Y, it's negative. So it's plus cosine 60 big I minus sine 60 big J, as we did last time. And the same for small j, you can convert it to big I, big J. So you can easily switch from one frame to the other, okay? Now, which frame to use? It depends which is easier. So for example, here, we want to determine the following terms. We have OC vector in our expression. We have also V relative, and omega here is along K. Small k and big K are the same. So if you look at vectors OC and V relative, both are along the rod, because vector OC is 0.2 times I, and V relative is 0.2 times small I. So here, for convenience, to have easier expression, it's easier to work in small I, small j. Because if you want to work in big I, big J, you should project OC and you should project V relative. So to simplify the analysis, we will express all vectors in frame small I, small j, small k. Okay? Okay. So now, once we do this step, we can do the vectorial calculation. So let us see in detail here. So first, we express all vectors. O is fixed, so the velocity of O is 0, and the acceleration of O is 0. Concerning omega and alpha, they are given, okay? So we should look at the figure to know if they are clockwise or counterclockwise. So if you look at the figure, you have that both are clockwise, as you can see here. So both are along negative k. So you can say that omega is minus 3k and alpha is minus 2k. Okay? Now, next step, I will replace into the vectorial relation. Okay? So let us do it together here if you want. So we will write that velocity of C, Vc, is equal to VO is 0, so 0, plus omega of the rod is minus 3k, small k or big K, it's the same. Vectorial OC is along I, it's 0.2 small I. So 0.2 small I. And plus V relative, the relative velocity is along the small I, it's 2. So plus 2 times small I. Okay. Now, if you expand K vectorial small I, it's plus small j, and you have minus, so it's minus 0.6 times small j plus 2 times small I. In this way, we calculated the expression of velocity of C. Okay. Now, next step, we want to determine the Coriolis acceleration and the acceleration of the column. So going back to our formula, in case of a rotating frame, we have developed a relation for velocities and acceleration. So this is the relation for acceleration, okay? In the acceleration term, you have first the acceleration of the coincident point. If you remember, what is the coincident point? It is the point of the rigid body on which C is located at this instant, okay? So because you have, this is rod OC, this is rod OC, and C now is on this point of the rod. So what will happen that the rod will give the velocity of this point and acceleration to the collar, plus we should account for the relative motion of the collar with respect to the rod. Okay, this is why in the expression of velocity, we have velocity of the coincident point plus V relative. And in the expression of acceleration, we have the acceleration of this point of the rod, which is AA plus alpha vectorial. So if we talk about C here, instead of A and B, you will replace B by C, and you will replace A by O. So point B is point C. Point A is O, okay, here. So when you do AO plus alpha vectorial OC, so when you do this, okay, plus, let me just fix this, plus alpha vectorial OC as vectors, of course. Now this term, if you remember, I told you omega vectorial OC, this term can be replaced in 2D by minus omega square OC. Okay, minus omega square OC. So until now, these three terms represent just the acceleration of this point of the rod. But to take into account the relative motion of the collar with respect to the rod, we have two additional terms. This is called the Coriolis acceleration. The Coriolis acceleration is 2 omega vectorial V relative. So it constitutes the effect of the relative motion, the relative velocity, and the angular velocity of rotation of the rod. Plus A relative, this term is A relative. So now all we have to do is to apply this vectorial relation in our problem. So first they asked for this component, which is the Coriolis acceleration. So all we have to do is to calculate 2 omega vectorial V relative. So if we go back to the problem, the Coriolis acceleration can be simply written as A Coriolis as a vector is equal to acceleration 2 times omega vector is minus 3k because it's clockwise. So 2 times minus 3k vectorial V relative. The relative velocity is 2 meters per second along the small I. So vectorial 2 times small I. Now we have k vectorial small I is minus j, sorry, is plus j, and we already have minus, so it's minus 12 times small j. This is the Coriolis acceleration. Okay, so now when we want to calculate the absolute acceleration of the color, we can use directly the result of Coriolis, which is minus 12j. So now as a final step, I will calculate AC. So I will apply the formula. AC is equal to, first, it's AO plus alpha vectorial OC plus alpha vectorial OC minus omega square times OC. So until now, this term represents what? It represents the acceleration of the point on the rod on which C is at this instant. So minus omega square OC. Now, to take into effect the relative motion of the color, I should add two terms. Coriolis, which is calculated now, A of Coriolis, 2 omega vectorial V relative, plus A relative, plus the relative acceleration of the color relative to the rod. Now I will start to replace. O is fixed, so AO is 0. So it's equal to 0 plus alpha of the rod. Of course, alpha and omega are characteristics of the rod, which is, if you want, the rotating frame is attached to the rod, so it will have the same angular velocity and angular acceleration of the rod. So our rotating frame will have omega equal to minus 3k and alpha equal to minus 2k because both are clockwise. So it's minus 2k vectorial OC. OC vector was found already. This is OC vector. The magnitude is 0.2 and it's directed along small I. So vectorial 0.2 times small I minus omega square. Omega of the rod is 3. So minus 3 square minus 9 times OC, which is 0.2 I. Now, for the Coriolis acceleration, we have just calculated it. We just replace A Coriolis by minus 12j. And concerning A relative, if we look at our figure, the relative acceleration magnitude is 3, and it's directed along the small I. Why? Because here the color is translating. No normal acceleration, just tangential one. And V and A are along same direction. So we have A is plus 3 along the small I. Now, all we have to do is to do the vectorial product here. So we have K vectorial I is J, and we have minus. So this will give us minus 0.4 J. And this term is minus 1.8 I. So in total, if we do the addition, okay, we will obtain along I minus 1.8 plus 3, so it's 1.2. And along J, we have minus 12.4. And in this way, we can get the acceleration, the absolute acceleration of C, which is the acceleration of C measured in the fixed frame. Okay? So if you are on the rod, you will just measure the relative velocity and acceleration, which are 2 meters per second and 3 meters per second square. But if you stand outside in the fixed frame, for the acceleration, you will measure the following result. And for the velocity, we have already calculated what is the velocity vector you will measure. So to summarize again, so the first step is to write our equations of our vectorial relations. We determine the terms that are needed in our calculation. So O is fixed, VO and AO is 0. We have the angular velocity and angular acceleration both are given and clockwise, so it's along minus k. And the relative motion is given, so V relative is 2I and A relative is 3I. Now all we have to do is to replace into the formulas, the vectorial relations, so we can get VC and AC, and both are absolute. So they are measured relative to, this is absolute values. So they are measured relative to big X, big Y, big J, big Z. Please don't confuse between, if it's in absolute velocity, even if it's absolute, you can express it in small I, small j, small k, because any vector can be decomposed into any frame. Okay, but the physical meaning of the vector هي إنه هي absolute velocity. So it represents the velocity that is measured by an occupant fixed to big X, big Y, big Z. Okay? Any question on this problem? Okay. Now we will do another problem. And if you remember this problem, we have done already this problem in chapter 12, in the first chapter of dynamics. And when we did it, I gave you a remark. I told you that when they asked the question in chapter 12, they asked for relative velocity and acceleration of B measured by A. And I told you this is possible to do in this chapter because A is translating. So since plane A is translating, when I want to measure relative to A, I can put a translating frame at A, and then relative to A, I can say that VB relative to A can be given by VB minus VA. But I told you, I gave you a remark, and I told you it's not possible to do the opposite. I cannot say that VA relative to B. So if I write VA relative to B, I cannot say that it is VA minus DB. Why? Because plane B is rotating. So if I put a frame on B, it will not be translating. If the plane is fixed, if the frame is fixed to the airplane B, it will rotate. It will not translate. So I cannot use VA minus DB for the relative velocity. I should use the updated formulation, which we studied in this chapter, which considered that if I have a rotating frame, in case I have a rotating frame, the formula will be as follows. So because the B is rotating, if I put a frame fixed to the plane, it will rotate with it. So I just take a frame small x, small y. At this instant, in the figure, the frame small x, small y, and big X, big Y are coincident. Okay, so you can have a certain instant where you can take them as coincident axes. It is possible. So always the choice depend on the situation. And for example, in the previous problem, كان من مصلحتنا ناخد small I along the rod to facilitate calculation. Here, the easiest choice for small x, small y هو إنه يكون horizontal vertical, يعني حيكون coincident with big X, big Y at this instant. Okay? So now, if I want to calculate the velocity and acceleration of A measured by B, يعني I am interested in V relative. In V relative of A with respect to B, and in A relative A with respect to B. These components, I can find them by writing the vectorial relation for rotating frames. Because for rotating frames, I have the following. I can write that V absolute of A is equal to V absolute of B plus, now, since my rotating frame is fixed to plane B, then I should add plus omega of B vectorial BA and plus V relative. So as you can see here, V relative is different than VA minus VB. V relative is affected by this term because omega is not zero. This is why we say that in case of translating frame, we don't have a problem because omega of the frame is 0. However, when we have a rotating frame, it will be different. Okay? So from this expression, we can say that V relative can be calculated as follows. It is the absolute velocity of A, VA, minus the absolute velocity of B, minus omega B vectorial BA. So we should also account for this additional term. Now, all we have to do now is to find the expression of the vectors to be able to calculate V relative. To start with, I will start with absolute velocity of A. If we look at the figure, it's given. So it is 700 kilometers per hour. For VB, so it is here, VA, we replace it by 700J. Here, small j and big J are the same, so it doesn't matter. So it's 700 times small j. Concerning VB, VB absolute is 600 J. Now, what about omega B? How can I find omega B is not given directly in the problem. I should try to find a way to calculate it. I want to calculate the angular velocity of rotation. So let me erase here. I want to calculate the angular velocity of rotation of the rotating frame fixed to plane B. Plane B is doing what? Is doing circular motion. Okay? And this circular motion is of known radius. So I know that the radius rho for airplane B is 400 kilometers. And I know that at this instant, when it is at this position, the velocity is 600. So since B is doing rotation about fixed axis, I can write that VB is equal to omega B times the radius R, the radius of rotation R. So I did use that omega B, just pay attention for units, okay? So here you have the velocity is given in kilometers per hour and the radius in kilometers. So at the end, your velocity, your omega will be in terms of, instead of radian per second, it will be in radian per hour. You can keep it in the unit of hour, it's fine. Okay? بس مهم to not mix units. يعني for example إذا هون بدل kilometers عطينا مثلا in meters, we should or transform both to meters or transform both to kilometers. Okay? So omega B is VB over R. So here it is equal to, the velocity is 600 over 400. So the result will be equal to 1.5 radiant per hour. Okay, so we can keep all units per hour, it's fine in this case. Now, once we got omega, we should also know its direction, if it's along positive k or negative k. Who can tell me here? Is omega along positive k or negative k? What should I apply?
Negative k.
Very good.
Right hand rule.
Yes, very good. So I apply the right hand rule. From the right hand rule, my omega will be clockwise. So vector omega b can be written as minus 1.5k. Minus 1.5k. Okay? So now I am ready to replace into the vectorial relation. Okay, let us do it together. So I have again V relative is equal to VA. VA is 700J minus VB, which is 600J, minus omega relative. Omega relative is 1.5K vectorial BA. What is vector BA? If I look at my figure, BA is along negative I, and the distance is, and the unit should be in kilometers because we are using units of kilometers and hour. So it's vectorial minus 4I. That's it. Okay. Now, this term we have minus minus plus, and k vectorial I will give us plus j, and 1.5 times 4 we have 6, so it's a plus, this term is plus 6j. So in total we have that V relative is 700j. So here all are along j. 700 minus 600, it's 100, and we have a 6, so it's 106. Okay, so V relative is 106j. Okay. Now, concerning the second step is to calculate the acceleration of B relative to A. So also we will apply the vectorial relation. Okay, so let us go to the details here. If I want to find the acceleration, I also should start from the vectorial relation. Okay, the vectorial relation, which is لحظة شوي, maybe let us check if
بس عامل
عاملين يمكن calculation error. Let us make sure. يلا خلينا نعيدها. قلنا VA equal VB plus omega vectorial BA plus V relative. اوكي, وقت اخذناهم للتاني ميل صاروا 700J minus 600J minus omega. نحن نسينا نحط الماينس again, يعني ماينس ماينس، مشان هيك طلعت ماينس. نسينا نحط الماينس مع انه قلنا انه هي نيجاتيف. That's it. غلطنا بساين ايرور. اوكي, يعني هي minus 1.5 لانه اوميجا is clockwise يعني it's negative. اوكي, نسينا نرجع نحط الماينس جوا. vectorial minus 4i يعني صار عندنا 3 ماينس مش 2. اوكي, this is why بيروحوا هول 2 الماينس. سو هون ماينس ماينس بلس بيبقى ماينس برا. اوكي, يعني بدل ما تكون بلس 6 بتصير ماينس 6. So the result for V is 94J. Okay. Now for the acceleration calculation, also we start from the general rule, which is absolute velocity of acceleration of A equals 2. So this is measured in big X, big Y, big Z. This is the absolute velocity, and this is the absolute acceleration of A. This is the absolute of acceleration of B. We will find them together. They are already, we have all information to find them, plus alpha vectorial BA. هيدا الفيكتور BA already لقيناه. So now we have something new اللي هو vector alpha. الأوميجا already لقيناها, and since it's 2D, we can replace this term by minus omega square times vector BA. Now, this is the Coriolis component with 2 omega vectorial V relative. نحن لقينا V relative from the previous step, it's calculated. We still have just the only unknown will be A relative. So when we take all the terms to the other side, we can get A relative. Now let us find together what are AA, AB, alpha, okay? To be able to replace them into the formula. If you go back to the figure, first, A is doing translation, so it only has a tangential component for acceleration. So we can replace in our vectorial formula AA, which is the absolute acceleration, measured with respect to the fixed frame, is plus 50 along J. This is for acceleration of A. Now, for point B, we just should pay attention that it's doing a rotation. So the acceleration of B will be decomposed into two components. Tangential one, which is given, it's along minus J. And we have the normal component. At this position, normal component اللي هو perpendicular to the velocity along the radius is along I. So I can write that AB vector can be decomposed into AB tangential plus AB normal. So I will add the components. For the tangential component, it's along minus J. So we have minus 100 J. Now concerning AB normal, how to calculate AB normal? Which formula we use?
V squared over rho.
Yes, very good. So plus the velocity is 600. So plus 600 square over the radius of curvature, which is 400. And it's directed along UN, which will pass through point O. So it is along I. In this way, we have calculated the components of acceleration of B. We still need to find what is alpha. What is alpha B? How to get alpha B, do you think?
AT over R.
Yes, very good, very good. So you know that in circular motion, you have that AT is equal to alpha times the radius. So I can say that alpha B as magnitude is AT over R. So I have, I will take the absolute value of the tangential acceleration. Okay, طلع magnitude first. And after, from the right-hand rule, I will determine the sense. So alpha B is AT, which is 100, over R, which is 400. So alpha is simply here 0.25. Now, also, I should use the right-hand rule to determine if it's clockwise or counterclockwise. Look at the figure. How will be alpha, clockwise or counterclockwise? Velocity is up, بس AT is down. يعني إجبار الألفا والأوميجا يكونوا opposite. بما إنه أوميجا كانت clockwise, so هون if you do the right-hand rule for alpha, it will be counterclockwise. So it will be along positive k. So we can say that vector alpha b now is equal to plus 0.25 k, not minus. Okay. Now we are ready to replace because we have found all new terms, AA, AB, alpha b. The other vectors, BA and omega, were already calculated in the previous step. V relative كمان we have found it from the previous step. So now all we have to do is to replace back into the formula. So just here we put instead of AA 50J, instead of AB 900I minus 100J, which are the components normal and tangential 1. Now alpha is replaced by 0.25K, and the position vector who will be A, we already found that BA is minus 4I. Now, as I told you, instead of doing this term, because it will need more time to calculate, you can just replace this term by doing minus omega square times vector BA. Let us try it. So it will give you omega is 1.5. So you will get this term is minus 1.5 square times minus 4I. So it will give you plus 4 times 1.5 square I. Okay? And concerning V relative, you just replaced V relative obtained in the previous step, PD94J, and omega is clockwise, so it's minus 1.5K. As you can see, the only unknown in this equation will be just acceleration of A relative to B measured with respect to the rotating frame. هيدي النوتيشن بس يحطوا small x, small y, small z يعني measured relative to this frame. Okay? While when they just put AB, هول الابسولute acceleration of points A and B. Any question on this? Okay. Now, كان فيهم يصعبوا شوي البروبلم if they give you, for example, a different position. And if they gave us the plane B here, for example, okay, ساعتها it will be easier to work with the IJK in another way. Okay, لأنه if you are here, for example, حاخد نفس الجيفن. يعني عندي 600 tangential acceleration, 600 velocity, sorry. والtangential acceleration negative, opposite to V, كمان 100. So I'll take same numbers but another position. Then, in this case, شو بيتغير؟ بس you will take a rotating frame in a way that will facilitate your calculation. Okay? يعني we can take then small I, small j, not coincident with big I, big J. ساعتها بنترك الفريم الابسوليوت like this. But for the rotating frame, we can put it in a way to facilitate the analysis. So you can take rotating frame هو fixed للairplane, okay? So you can take small I, small j like this. So small I will be along UN. Small j will be along UT. This will facilitate for you the calculation للاcceleration in this frame. Okay? وبيكونوا عاطينكم الانجل, for example, انه the angle with the radius at this position, let's say, is 30 degrees. Okay. Now here you can select any frame to work with. يعني فيكم تنتقلوا بسهولة من small I, small j ل big I, big J. So for example, if you want to calculate the V relative, okay? The V relative شو كانت الexpression تبعها؟ V relative is equal to VA minus VB minus omega vectorial BA. Okay? Now, what will be different شوي هون I will have first they should give me الفيكتور هيدي البوزيشن يعني فيكتور AB المفروض يعطوني الكوردينيتس تبعه. Okay, so I should know, if you want, what is this distance, and what is this distance. Okay, هلا now you can choose to work in any frame. يعني فيكم تشتغلوا كل شيء ب I big I big J، فيكم تشتغلوا كل شيء ب small I small j. It depends on what you want. اوكي، هلا هون مثلا اثنيناتهم فيهم شويه complexity لانه في vectors بس along small I small j، بس في vectors ثانيين along big I big J. يعني in both cases I should do projections. So it's up to you. يعني مثلا if I consider V relative, the expression of V relative. أول شيء vector VA is along big J. يعني إذا بدي أكتب الexpression of VA بعدها 700 times big J. هلا now for vector VB هو along small j. يعني إذا بدي أحطه مثل ما هو plus 600 في minus قبله، so minus 600 times small j. okay، بس of course ما فيني اترك الاديشن هيك، يعني I should أو express big J function of small I small j أو express small j function of big I big J، بس ما فيني اجمعهم مثل ما هن هيك. so pay attention. okay، now minus الأوميجا بعدها along k، الأوميجا ما تغيرت بعدها clockwise. اوكي، وبعدها along positive k، يعني بعدها minus 1.5k. now for BA حنشوف BA شو أهين لنا نعمل له decomposition. for BA أهين لنا نشتغل ب big I big J because look هن عاطينكم هول الdistances. يعني let's say for example هيدي 2 kilometers for example وهيدي 5 example، عم بعطي حيلا numbers. okay، ساعتها vector BA can be decomposed into it has a negative component along I و negative component along J. So I can replace vector BA by minus 2 big J و minus 5 big I. فإذا بتلاحظوا أغلب الترمز عندكم هن big I big J، بس you have just one term along small j يلي هو ال VB. ساعتها أكيد أهين لي أعمل conversion من small I small j frame ل big I big J. لو كان العكس كنا ضلينا نشتغل كل ال projections ب small I small j. أوكي؟ يعني أنتوا you select what is easier for you إلا إذا هن جبروكم. يعني they might tell you express your vector function of small I small j small k. ساعتها you should after doing the calculation بتقولوا إنه I will express big I big J function of small I small j and just I do the replacement. How I express them? It's very simple. بتطلع على الفيجر. This is big I big J. Now إذا بدي أرسم هون ال small I small j, this is small I and this is small j. And the angle here as you can see between small I and big I هو 30. So this is 30 degrees. So now I can easily do the decomposition. يعني فيني أقول إنه small I has a positive projection along big I and negative projection along big J. So it's equal to cosine 30 times big I and minus sine 30 times big J. Okay. And also I can express small j. So if I look at small j now, it has positive projection on both. And for small j, it's equal to plus sine 30 على I و plus cosine 30 على j. Okay. And in this way, I can switch from one frame to the other in a very simple way. Okay? Any question on this? So this is chapter 16. We are done with chapter 16. We will start to do review problems together on this chapter. Okay? Do you have any question before we start the review problems? في شيء مش مفهوم أو sections قبل if you want also. Do you see the PDF now?
Yes, doctor.
Okay. So let us start with the first problem. The following disk is moving to the left such that it has an angular acceleration alpha and an angular velocity omega at the instant shown. If it does not slip at A, determine the acceleration of point D. Okay, so now we will try to think which method to use. Here we have a disk. It's one rigid body, okay? And we don't have any point with relative motion with respect to the disk. And عندنا one rigid body, and all points are on the body. So we will use the vectorial relations relating acceleration and velocity on one rigid body, okay? Now, it's a disk, and it's rolling without slipping. Whenever we have non-slipping condition and the ground is fixed, يعني the point in contact with the ground VA عنده zero velocity وعنده tangential acceleration zero. If you remember, yes, last time also we have seen this remark إنه tangential acceleration هي ذاتها مش total acceleration because the ground is fixed. يعني إذا باخد الpoint on the ground إذا بسميه G, okay, the acceleration of G is zero. But the acceleration of A is not zero because AA has two components. في tangential one, and if I talk relative to C, في عندي tangential component, في عندي normal component. So I cannot say إنه the acceleration of A is zero. وثبتنا أنا وياكم last time إنه the acceleration of A بتكون equal to omega square times R, radius of the disk, okay, times UN بيكون directed from A towards the center اللي هي هون J. Okay, so because of this I should pay attention إنه ما أحط AA zero. Now, if I am interested in finding the acceleration of D, I have two possibilities. I can relate to A or I can relate to C. اثنيناتهم صح. But C is easier for me because I know vector CD, I know the angle phi. بينما for vector AD بدي أعمل extra calculation to decompose vector AD. Okay, so what I can do, since it's easier to work relative to C, وC هو أهين point بالdisk لأنه the motion of C is rectilinear. And since I have rolling without slipping, I can directly write إنه velocity of C is in magnitude equal to omega times R. This is the magnitude of velocity. والdirection هي حسب ال right hand rule. بما إنه A هو ال instantaneous center, since omega is counterclockwise, the velocity should be to the left. So I can write that VC vector is minus omega r along I, and AC vector, since C is always moving along a straight line, يعني ما عنده إلا tangential acceleration, and at any instant it's the derivative of velocity, with derivative of omega هي alpha, and r is constant, so AC is minus alpha r along I. كمان it's minus لأنه الألفا as you can see here is also clockwise. فيها تكون الألفا counter clockwise إذا عنا deceleration، ساعتها بتصير ال AC plus alpha R. Okay? So now, since we know alpha is 8, we know the radius, يعني acceleration of C is minus 4I. AC is minus 4I. Okay? Now, all I have to do to calculate the acceleration of D is to relate the 2 points. So I will write the following. هلا just for the notation of the problems حفصلكم هن كيف بيشتغلوا. هن just instead of writing vector ijk بيحطوه in, they represented in a column. Okay? And this component هيدا الفector مثلا هو vector AC. بدل ما يكتبوا انه AC هو equal to minus alpha ri plus 0j plus 0k, okay? بحطوهم in this way. So this is I component minus alpha r. Since no components along j and k, يعني 0, 0. Okay? So this term represent AC. Plus, شو بتقول الفورمولا إذا عندي 2 points on one rigid body? AD equal AC plus alpha vector vectorial CD على طول ببلش من البوينت اللي أنا عم بشتغل relative to it to the other point اللي عم لاقي له الأكسلريشن، يعني CD هو الفector. So plus alpha vectorial CD. Now هن in general بيستعملوا الcomplex relation، فيعودوكم عليها ل 3D اللي هي omega vectorial. بس بليز انتبهوا اذا بدكم تعملوا هاي الفورمولا بدكم تنتبهوا للاوردر. اوكي؟ يعني انتبهوا للبراكتس. بعمل اوميجا سي دي لحالهم هول بيعطوني الفيكتور، برجع بعمل اوميجا فيكتوريال ريزلت. بس بما انه عم نشتغل نحن 2 دي، ليش تتعقدوا القصه؟ You can replace this term by minus omega square times CD vector. Okay? Now, let us find what are the vectors that are missing for us. AC جبناه سوا، بعد بدنا نجيب alpha و CD و omega. So let us look at our figure. Concerning alpha, alpha also is counterclockwise. So it's along positive K. So alpha is equal to 8K. Alpha is equal to 8K, and vector CD can be decomposed into 2 components, one along I, one along J. So we can write vector CD as the radius is 0.5. Okay, so if we project, we can say that vector CD is equal to 0.5 times cosine phi along I plus sine phi along J plus sine phi along J. This is vector CD. And phi we replace it by the value which is 45 degrees. Okay. Now all we have to do is to replace back into our relation. So it becomes very simple. Okay, خلينا نعملها. We have AD vector. أنا حأعملكم الميثود تبعنا وهن عم يعملوا الcolumn representation. Okay, so AD equals to minus alpha times R is 4, minus 4 along I plus قلنا alpha is clockwise يعني plus 8k vectorial vector CD we will replace by its value اللي هي 0.5 times cosine 45i plus sine 45j minus omega square. انتبهوا بالماينس اوميجا سكوير منه فيكتور هو نمبر. اوكي في كثير بيعملوها فيكتوريال. نو اتس ماينس اوميجا سكوير كنمبر يعني ماينس 3 سكوير هيدا نمبر تايمز يعني multiplication عادية تايمز الفيكتور سي دي يعني تايمز 0.5 تايمز this term هيدا بنحطه هون again 0.5 cosine 45i plus sine 45j. And now all we have to do is to expand. يعني بنعمل k vectorial i هي plus j, k vectorial j هي minus i. Then we take the I components together, the j components together, and we can calculate then the acceleration vector. هلا إذا طلبوا منا الماgnitude with direction, it's very simple. The magnitude is radical 10 square plus 0.35 square. وبالنسبة للdirection, it's in the fourth quadrant, in the third quadrant. So إذا بتعملوا لها representation هيك, it has negative I and j components like this. So you can say if I want to calculate the angle theta, I can calculate theta with the horizontal axis. فبعمل tangent minus 1 of the absolute value of y component over x component. Okay, any question on this problem? Let us start with another problem. The planetary gear system is used in an automatic transmission for a car. By locking or releasing certain gears, it has the advantage of operating the car at different speeds. Consider the case where the ring gear R is rotating with angular velocity omega r and the sun gear is fixed with omega s equals to 0. Determine the angular velocity of each of the planet gears P and the shaft A. So here we have a system of gears that are connected together, and we want to determine how the velocity of one will affect the other. Okay, so this system is widely used in cars. What is the principle? The principle of it is that we can control the speed of gears if we play with two of the gears. And for example here, if we fix in this problem, we fix the sun gear. This one here is fixed, but we can move it if we want. Okay, and we will see that if we move it, we can control velocity, angular velocity of the planetary gear P. Okay, but here in this problem, we choose to fix it. So omega s is equal to 0 in this case. And what we are doing is that we impose a certain angular velocity for the ring, which is the external gear, the big gear here. We impose on it an angular velocity of 3 radians per second. Okay, so omega r is equal to 3 radians per second. Now, our purpose is knowing these two, yani knowing omega s and omega r, we want to determine what will be omega a, which is the shaft here, what will be omega a, and what will be the angular velocity of the gears, of the small gears P. What is omega P? This is the question. And you will see here that by just controlling these two, you can impose a variety of speeds for the shaft and P. From here, the importance of the application. Okay, so now, the first step to do is to try to look at the figure. If we look at the figure, since we are interested first in omega of p, okay, whenever you have a rigid body and you want to find its angular velocity, you should try to determine the velocity of 2 points. Because if you know the velocity of 2 points of it, you can just find omega easily, or by the vectorial relation, or also by the conventional method, which consists on calculating just omega by doing the right-hand rule with principle of, if you want, instantaneous center also. Okay? So let us consider the planetary gear and see what are the velocities that we know. We have that this gear is in contact first with the sun gear and second with the ring gear. And these two velocities will be known because we don't have slipping in gears. Whenever I have system of gears in general, we have non-slipping conditions. And when we have non-slipping conditions, this means at the contact point we'll have the same velocity. So here you can say that if we call this point A and we call this point B, we can say that the velocity of A as a point of the sun gear is equal to the velocity of A as a point of gear P. And since the sun gear is fixed, then we can say simply that the velocity of this point is 0. So now we know the velocity of point A, and since it's 0, so this is the IC. This is our instantaneous center. Now, concerning point B is in contact with the big gear. So we can write that velocity of point B as a point of the big gear is equal to the velocity of point B as a point of the planetary gear P. Now, we can find this term because the big gear is doing what? What is the type of motion of the big gear? Look at the figure. البيج gear شو عم يعمل؟ It is translation, it is rotation about fixed axis, or it is general motion?
دكتور انت عم تحكي عن R ولا R2؟
عن R. big R هيدا الديسك الكبير. اوكي هيدا هو كله شو عم يبرم هيدا؟ شو عم يعمل هيدا الديسك؟ طلعوا عنا
مش circular
لانه عم يبرم around a shaft of center S. يعني center of S هو ذاته center of R. لانه لاحظوا هون هو عم يبرم هلا مزبوط هو منه full disk اوكي بس الاكسس تبعه وين حيكون passing by the center of S. يعني اذا باخذ الاكسس of the shaft it's passing by the center of the gear S, okay, and it is also the center axis للبig gear. يعني البig gear is doing rotation about fixed axis, okay, because of
دكتور
this. نعم
بس مش هي عم تعمل circular motion بس لانه هول الصغار اثنيناتهم equal لبعض الراديوس.
لا ما خص ما انت هول الصغار ايه هلا اجباري يكونوا الراديوس مثل بعض والا ما بيقدر يعمل روتيشن اباوت فيكس اكسس اكيد اوكي بس لانه انت عندك كل البوينتس هن equidistant from center يعني الجير ار كل البوينتس تبعه equidistant from the shaft هو عم يعمل روتيشن حيكون عنده روتيشن about fixed axis اوكي بينما اذا بتاخذ السمول جير ما عم يعمل روتيشن about fixed axis عم يعمل general plane motion لانه هو شو عم يعمل حيبرم around its axis وزياده حيعمل translation يعني اذا بتطلع بالسنتر بالسنتر تبع السمول جير شو رح يعمل السنتر رح يبرم
حيمشي in a circle السنتر وهو بنفس الوقت بيكون
السنتر حيمشي على سيركل والديسك حيبرم حول حاله بنفس الوقت يعني هول الاثنين الجير بي هن general motion بينما البيج جير اوكي البيج جير بس عم يبرم around its axis صح؟ لانه حاطينه بطريقه انه عم it is rotating about the axis passing by its center بس ما عنده another relative motion because this axis is fixed. Okay, so we can say here
Yes.
الأوميجا R ال R is doing rotation about fixed axis. الشافت كمان الشافت A هيدا كمان عم يبرم it's rotating about a fixed axis. الوحيد اللي عنده general plane motion هو ال P لأنه مثل ما قلنا الاكسس تبعه منه fixed، يعني إذا باخد axis passing by its center هيدا الاكسس عم يمشي لأنه O is moving، وبنفس الوقت الجير عم يبرم about its axis، يعني عندي general motion in this case. Okay, now going back to this point ل point B. إذا بدي لاقي ال velocity of this point what is the method؟ بس يكون عندي rotation about fixed axis. All I have to do is to take the total distance from the center of the sun gear to the point B. لأنه center of sun gear هو الأكسس، هو بيمرق فيه الأكسس of rotation. هيدا distance to B is equal to what؟ هقسمها ل parts. I have first the radius of the sun gear and I have here 2 times the radius of gear P. يعني in total I have R of S plus 2R of P. Okay, so if I draw my gear P هيدا الجير P okay عنده point of zero velocity at A VA equal to 0 بينما for point B here تعرف ال direction بدي اعمل ال right hand rule. point velocity اكيد perpendicular للراديوس وبما انه omega is counterclockwise يعني VB will be directed towards the left and I can write that VB is equal to VB بجيبها من قلنا من الروتيشن تبع سوري بس هون اوميجا هيدي اوميجا بي عم بحكي عن البلانيتري جير انا هلا اوكي بس انا تعرف لاقي البلانيتري جير اوكي المفروض جيب في بي فانكشن اوف اوميجا ار يعني انا وقت اطلع بالبيج جير في بي هون كيف فيني اكتبها في بي بدها تكون perpendicular للراديوس واجباري تكون to the left لانه اوميجا ار is counterclockwise ففيني اكتب في بي ك equal to omega r times the total distance to the center يلي هي 2rp plus rs so times 2rp plus rs. Now since I know now the velocity of point B هستعملها now كpoint B كpoint on P because you know انه VB فيني اكتبها بطريقتين فيني اقول انه B is a point of R يعني ساعتها VB is equal to omega R times the big distance to the center of to the axis اللي هي 2rp plus rs بس كمان فيني اقول انه B is on small gear P يعني فيني اكتب ال VB تبعه بغير طريقة اللي هي equal to اذا بتطلع بالبلانيتري جير وين ال instantaneous center هون so VB should be equal to omega P times distance to the instantaneous center اللي هي 2rp. So now I can write that omega r times 2rp plus rs is equal to omega p times 2rp. وas you know إذا بتطلعوا بالgiven مع ال rp وال rs ومع ال omega r يعني the only unknown will be omega p. In this way I can calculate the angular velocity للبلانت جير P. في حدا ما فهم كيف جبنا omega p? Please tell me, I can repeat if you don't understand. طيب, what is the next step now? طلبوا مش بس ال angular velocity of P، كمان طلبوا ال angular velocity of the shaft A. مين بيقول لي طلعوا بالفيجر كيف فيني اجيب ال angular velocity of the shaft؟ هيدا الشافت بدي اجيب اوميجا of shaft A. أول شي شو عم يعمل الشافت؟ Which type of motion؟ The shaft is rotating about a fixed axis. صح؟ هيدا الأكسس تبعه. يعني تقدر جيب أوميجا A I should try to find at least just velocity of one point of the shaft. مش ضروري الشافت يعني ما هو الشافت is connected to this part. يعني إذا بلاقي ال velocity of any point on this part بصير فيني جيب الأوميجا of the shaft. طلع منيح. أي point على هالفيجر بقدر جيب الفيلوسيتي تبعه تقدر جيب اوميجا A. هذا الشافت is connected to what?
Center of P.
Oui, very good. It's connected to the center of P. يعني أنا إذا بقدر جيب ال velocity of center of P تنحل المشكلة تبعي. هسميه point C. أوكي؟ كيف فيني أجيب ال velocity of C؟ رح أرجع للplanetary gear P. أنا بالنسبة ل P شو جبت؟ هيدا السنتر تبعه سميناه C. أنا بعرف إنه ال instantaneous center is here. فتجيب الفيلوسيتي وبعرف اوميجا بي جبتها معي اياها اوميجا بي. So I know from the instantaneous center method إنه ال velocity of C هتكون perpendicular للdistance joining C وال IC. وبالنسبة للdirection I can know it from the right hand rule. I can know it from the right hand rule. So because omega is counterclockwise, then V should be to the left in order to have rotation in the counterclockwise direction. So I can write that VC is towards the left, and in magnitude, it's equal to omega P times the distance between the C and IC, اللي هي radius of P. So I can say that VC is simply equal to omega P times RP. Now, C is common between gear P and the shaft. يعني فيني اكتب VC بغير طريقة. يعني على طول هيدي الidea in this problem. I express the velocities in two ways طلع ال unknown تبعي. أول way as a point of P هي equal to omega P RP. وتاني method as a point of shaft A. So it's equal to VC as a point of shaft A. So now if I take C as a point of shaft A, I should multiply omega of the shaft by which distance? It's omega A times which distance, guys? طلعوا بالفيجر. هيدا الشافت تبع A. مظبوط؟ بدي اخد the distance from C to the shaft. This one. يلي هي equal to the radius of the planetary gear. يعني عندي this part plus the radius of the sun gear. يعني in total the distance from C to the shaft to the axis of shaft A هي RP plus RS. RP plus RS. So now عندي كل شيء إلا omega A. So I can find omega A. So I can just say simply إن omega A is equal to omega P times RP over RP plus RS over RP plus RS. Okay. Any question on this? Okay. Another problem. The mechanism for a car window is shown in the figure. Here the handle turns the small cog C, which rotates the gear S, thereby rotating the fixed connected lever AB, which raises track D in which the window rests. The window is free to slide on the track. If the handle is wound with angular velocity omega, determine the speed of points A and E and the speed of the window at the instant tap. So let us look at the figure here. What do we know in this figure? First, you have a small head mechanism that is used to open and close windows in old cars. Okay? So first, you have here a small gear on which you can impose angular velocity omega c by just putting your hand. يعني انتوا بس تحطوا ايدكم وتبرموا, you can impose the angular velocity of the small gear. Okay? Now, the small gear is connected to a bigger gear, which will give us a certain angular velocity for gear B. How we can relate the two gears to find the angular velocity of B? نطلع بالcontact point. For the contact point, since we don't have slipping, إذا هيدا الpoint of contact سميناه O, okay? We can say that the velocity of O as a point of gear C, so velocity of O as a point of gear C is equal to velocity of O as a point of gear B. If we look first at gear C, VO as a point of C can be written as RC times omega C. So this is RC times omega C. And velocity of O as point of gear B is equal to RB times omega B. So from here we can deduce that the magnitude of omega B is equal to RC times omega C over RB. Now, next step, انتبهوا على الدايركشن. اوكي؟ هون ال V is the same بس الأوميجا حيكونوا opposite. You know why؟ لأنه عملوا الرايت هاند رول. إذا أوميجا عم يبرم clockwise، إذا بعمل الرايت هاند رول على gear B will rotate counterclockwise. So you can say here just you put the magnitude وبتحطوا حدها ال true direction اللي هي counterclockwise. So we have calculated here, until now, we have calculated omega B. Next step, our purpose is to find شو هي ال velocity على الويندو يلي حتعلي وتوطي الويندو. اوكي؟ هلا بالويندو شو بيصير؟ نحن عندنا هيدا الرود, this rod is connected to الجير B, يعني حبتبرم مع الجير B at the same angular velocity omega B. Okay? So here we have the angular velocity of B. We have already calculated it. So we can deduce what will be velocity given to point A. هلا انتبهوا على شغله. Velocity at A هي perpendicular to the radius. والradius هو AB. Okay? This is your radius. So you can calculate the velocity that is given على A. بس أي component من velocity هو اللي بيطلع الويندو؟ أكيد مش component اللي هو horizontal. بس vertical component هو اللي بيطلع الويندو. يعني velocity of the window هتكون equal to the projection of the velocity of this point along the vertical. This is why the first step will be to find what is the velocity that is imposed على A. وبيرجع we project this velocity on the vertical to get what will be the component of velocity على الويندو. Okay? So now to get first the magnitude of VA, all we have to do is to multiply omega B, omega of gear B, by the distance from B to A. So it's omega B times AB. Okay? In this way, we can get the value of the velocity. Now, in order to project, we should know this angle. Okay? If you look at your figure, they gave us the angle theta between the horizontal والarm. This is theta, okay? And as you can see, the window velocity is vertical, يعني perpendicular to the horizontal. Well, velocity of A is perpendicular to arm AB. يعني صار عنا whole two lines are perpendicular to these two lines. So we can deduce إنه the angle here is equal to this angle is equal to theta. So this angle is theta. So all we have to do now to find the velocity of the window is to multiply VA by cosine of theta. Okay? Any question on this? Okay, so let us start a new problem. When the bar is at the angle theta, the rod is rotating clockwise at W and has an angular acceleration alpha. Determine the velocity and acceleration of the weight A at this instant. The cord is of length S. So let us look at the figure. What do we know here? We know the motion of the rod BC. So for rod BC, we know that it's rotating and we completely know its motion. We know its angular velocity and we know its angular acceleration, omega and alpha. And both are counterclockwise. Alpha and omega are both counterclockwise. Now, our purpose is to determine what will be the velocity of A and what will be the acceleration of A. So here, you have, if you want, a type of dependent motion here, because the rotation will impose the translational motion of A. Whenever you have such dependent motion, you should think of relating if you want, the parameters of motion of CB to the parameters of motion of A. So you should relate theta omega alpha to SA, VA, and AA. Okay? And of course, this will be possible by first relating SA to theta. So the first step in such problems will be to find the geometrical relation between SA and theta. Once I have the geometrical relation between SA and theta, all I have to do is to derive. I derive the first time, I get VA, function of my parameters. I derive a second time, I get alpha A, function of my parameters. So to start with, let us look at the figure and try to relate our angle theta to the value of SA. First, if you look at your figure, what is fixed in your figure are the following parameters. The distance between D and C will not change. This is A. The length of your rod is constant also, it will not change. So A, B are fixed. What is varying is BD. So this distance is varying with SA. Okay? So if we call this distance, so this is SA. Because it's a chord of constant length, we can say that dB can be just written as the total length of the chord minus SA. And of course, dB will be variable since theta is varying, which will affect then the value of SA. Now, if you look at your figure, in order to relate L minus SA to theta, you can just apply the cosine law, because from cosine law, you can write the following. You can write that dB square, which is L minus SA square, equal to a squared plus b squared minus 2 times a times b times cosine of theta. In this way, you have found a relation between SA and theta. Okay? Look, what I advise you is to derive it as it is because it will be easier to derive. Because إذا بتاخدوا الراديكال يعني إذا بنعمل radical for both sides بتصير more complex derivation. هن راحوا للميثود that is more complex. بس أنا هعمل أنا وياكم the easier method. Okay? So always derive the simplest relation أحسن ما يكون عندكم radical و complex derivation. So let us derive this relation with respect to time. If I derive this relation with respect to time, what do I get? First, hey, the function u, okay? If I want to derive it with respect to time, بعمل chain rule. يعني أول شيء I derive with respect to s, برجع بضرب b ds by dt, okay? So what is the derivative of this function? Derivative of this function حتكون minus 2 times L minus SA وأكيد تحولها لدerivative with respect to time by using the chain rule. I multiply by dSA by dt. And what is dSA by dt? It's the velocity at A. So minus 2 L minus SA times VA equals to, when I derive the other side, this is a constant term, derivative 0. I should just derive this term. And you know that the derivative of cosine theta here minus sine theta. وعندي already minus, so بيصير عندي plus equals to plus 2ab times sine theta. وما تنسوا انه لحديت هلا عملنا derivative with respect to theta بس نحن بدنا نعمل derivative with respect to time. So we should multiply by theta dot اللي هي omega. So as you can see here, طلعنا relation between SA and theta and VA and omega. Okay? So if you rearrange your terms now, يطلع لكم the expression of VA. Okay? هن بس رجعوا عملوا replacement. So you get VA function of these parameters. Okay? Now, to get a relation between acceleration, all you have to do is to derive again this relation with respect to it. Okay? So now, if I derive this relation with respect to time, I can get the expression of AA function of alpha. Try to do it. Okay. فيكم تستعملوا their method أو فيكم تعملوا derivation للإيكويشن اللي نحن طلعت لنا. So you can get the expression of VA and AA function of theta, theta dot, omega and alpha. Okay. Any question on this? Okay, so we continue next time, okay? Bye-bye.
Thank you,
Merci,
doctor.
doctor.
Welcome back.
Thank you, doctor.
Thank you. Goodbye.